Okay, the second talk is by Joe Paat, and the title is The Integrality Number of an Integer Program Sequence. And that's it. Sorry. The integrality number of an integer program. The schedule is all run up. Okay, go ahead.
I see. Thanks, Dan. Can everyone hear me? Or can someone hear me at least?
I can.
Okay, yes. Great. Well, first I want to say, again, congratulations to Kim. I guess it's a great honor to win the first Best Paper Award, so nice job. And now that Ahmad's awake, I also want to thank the organizers. IPCO's always been a great conference, and Quarantine Edition is no difference, at least not yet. So thank you guys very much. So this is some work that I did with Miri and Robert Wisemantel in Zurich. And this notion of an integrality number I'll get to in a moment, but sort of the goal. Oops.
Just sorry to interrupt, but we cannot see your slides.
I see. Let's see this then. Is that better?
Yeah, that looks good.
Great. Yeah, sorry about that. So, like I said, this is work with Miri and Robert from Zurich, and let's see. Okay. So the overall goal of this project was to take an integer hull of the points inside of a polyhedron and model it as a mixed integer hull with as few integer constraints as possible. Okay. So what do I mean by this? Just sort of with a picture to get an idea. Well, here on the left, I have this red triangle, this polyhedron. And if I impose integrality on each component of the points individually, then I recover these three integer points, and the integer hull is just this dashed region. Okay. So you can ask, well, what happens if you drop one of the integrality constraints? Well, then we get this mixed integer set. And here again, I've highlighted the mixed integer hull. And in this, we see that, well, it's not the same as the integer hull because we have some extra points that fall into this mixed integer set. But if we were a bit more creative with how we introduce integer constraints, suppose we only want the sum of the variables to be integer, then in this particular polyhedron, the points that satisfy this condition, again, form the integer hull. So here, what we can see is that in this example, we can actually model the integer hull as a mixed integer set, but only using one integer constraint as opposed to two. Okay, and this is the overall goal motivating our talk or our project. So the main object that we use is this notion of a mixed integer relaxation. Okay, and so all of these red sets above, without the convex hull, these are all what I'm going to be calling W MIPS, but you can just think of them as the points inside of some polyhedron that also satisfy some linear forms that we require to be integral. Okay, so this W, typically it's the identity matrix or some part of the identity matrix, but as we saw in this fourth example, we don't need this to be the case. We can actually just assume, we can be a bit more creative with how we introduce integrality here. Okay. So why are we interested in modeling the integer hull? Well, perhaps for many reasons, but the reason that we are interested in for this talk is that if you give me any of these mixed integer relaxations and you take the convex hull, then you can find a vertex of this convex set in this amount of time, so about 2 to the k squared. Okay, and this is something that follows from Lenstra's algorithm with a little bit of extra work. Okay, so if we can possibly take this integer hull, model it as a mixed integer hull with fewer constraints, then by this result of Lenstra, we can find an integer point more efficiently, at least in theory. Okay. So this leads us to our definition of the integrality number. Oh, and by the way, if you can't read my handwriting, please let me know. So we define the integrality number of a polyhedron as the fewest number of constraints, integrality constraints we need to define a mixed integer hull that's equal to the integer hull. And so in this example that we started with, if we don't add any integer constraints, then we're left with our original polyhedron, which is not the integer hull. But as we saw, we can get away with only adding one constraint. Okay, so here the integrality number would be 1. So there's a few sort of easy to see upper bounds on the integrality number. One of them is that the integrality number is always upper bounded by the dimension. We can always add sort of these standard integer constraints, and of course we will recover the integer hull. Okay, so the integrality number is always bounded by n, upper bounded by n. Another special case that we know is if our polyhedron is what's called, or if our matrix A is what's called unimodular. Okay, so for this, I'm going to define a parameter delta, which depends on A, so delta of A. And this is the largest full rank matrix minor inside of A. Okay, and I didn't state this, it was written on the slide, but I'm assuming A has full column rank, so A has rank n. Okay. So if this delta happens to be 1, then every vertex of our original polyhedron is already integer, and so we don't need to add any other constraints, and we see that the integrality number is 0. Okay. So here are 2 special cases that we can, where we can understand the integrality number a little bit. And so our goal is to bound the integrality number, and in doing so, kind of explore the trade-off between these parameters n and delta. So delta is, I mean, many of you have explored this parameter delta to some extent, but in recent years, it's been a topic of interest in IP theory, sort of how this delta affects our ability to solve integer programs. And as I underlined here, I'd like to do this constructively. In the future, I would like, well, we would like to see how our relaxations, how computationally effective they are. And even Robert has interest in this. And if Robert's interested in computational results, then you know it must be interesting. Okay, so there's been a lot of work on describing integer hulls as mixed integer relaxations or reformulations. And perhaps the most relatable piece of work to ours is a project that was completed by Botter et al. In 2017 on this notion of the affine TU dimension of a matrix. Okay, so if you're not familiar with what this is, you can just think of it as another way of reformulating an IP as a MIP. And what they showed in their paper is they collected a bunch of interesting examples, and they also discussed some complexity results, but they, at least to my knowledge, they don't really provide a general framework for creating these MIP relaxations. And one thing that we try to do in our paper is provide some sort of general construction to be used. Another thing that I just want to briefly mention about this TU dimension is that it's not invariant if we take our polyhedron and we map it by a unimodular matrix. So why am I highlighting this? Well, if we're interested in the integer hull, then this is an object that is, I mean, if you map an integer set by a unimodular matrix, it remains integer. And in some sense, the number of integer constraints you would need to describe this hull shouldn't matter if you transform it. Okay. So another piece of work that I'd like to mention is a recent paper by Afonso Ceballos, Stefan Welke, and Rico Zenklusen that appeared in SOTA a few years ago. And they considered mixed integer extended formulations. And that's a very interesting paper, but just to highlight one result, they show that even if we change this delta parameter from 1 to 2, then you can find examples of polyhedra where the integrality number is already square root of n. Okay, so going back to this goal of understanding the trade-off between delta and n, even when delta is 2, we can't hope to get something independent of n. And this here would be, personally, I think it would be interesting to see if their example can be generalized to larger values of delta, but that's future work. Okay, so how do we go about bounding the integrality number? Well, we use the following helpful lemma. And this helpful lemma, as we'll see in a moment, is a generalization of variable aggregation. Okay. So suppose you have a matrix C, and you have sets capital B and capital T, such that the set of columns of C, so C can be it can have many, many columns. Think of n as much bigger than S. And if you look at the set of unique columns, suppose this is contained inside of this Minkowski sum, B plus T. Okay, so here I have a few examples. Suppose these black dots represent the distinct columns of C. Here I've highlighted in red my choice of B. So here I have sort of 7 points in my set B. Here I have only 4 points in my set B, but if I use this extra translation vector, I still cover all of my black points. Okay. So suppose you have this C and this B and this T. Then if you take a matrix that's formed like this, so it has the C as part of the matrix, and then you can add identity rows, then the integrality number of any polyhedron with this constraint matrix is at most B plus T, the cardinality of B plus the cardinality of T. Okay, so here, I mean, if again these were our columns, then we can bound the integrality number by 5. Are there any questions on this? Okay. So, like I kind of hinted that this is related to variable aggregation. So I want to sketch a proof of this lemma from the point of view of aggregation. And for this, I just want to use an example. So I'm going to consider this matrix C, which has 8 columns, but I mean, 2, you see that they're in groups of 2 that are all the same. And I'm going to consider this knapsack, 1-row knapsack polytope. Okay. And B here, it can be whatever you want it to be. So it's kind of a folklore result that if you want to model this integer Hall, you can do so by aggregating equal columns. So what do I mean by that? Well, this constraint matrix, or these integrality constraints, what they do is they take the first 2 columns, which are equal, and they require that x1 plus x2 is integer. Okay, this is what I mean by aggregation of equal columns. And so on and so forth. I mean, we take every set of columns that are equal, and we require that the sum of these variables is integer. If you're not familiar with this equation here, I'll try to motivate it on the next, or I'll try to explain it on the next slide. But what we see is that given this matrix, if you believe that this equation is true, we already see that the integrality number for our knapsack polytope is at most 4. Okay, it's at most the number of distinct columns. So here we have a nice totally unimodular or TU matrix, and that will be important in a moment. But let me try to rephrase this variable aggregation from the point of view of this lemma. So let me kind of re-argue this using the language that I set up in the lemma. So again, I'm going to choose my box B, or my set B, to be all of the distinct columns of C. And I'm going to set my T, or my translation set, to be empty. So of course, I mean, the set of columns is contained inside of this Minkowski sum. And this inclusion can actually be written in matrix form. So we can actually take C now with possibly repeated columns, and we can write it, I mean, if we take the columns of B and T and put them in a matrix, we can write C this way, as this matrix times TU matrix, and this is the TU matrix that we just saw. And the size of this TU matrix, at least the number of constraints, is B plus T. So we can sort of see where this B plus T is coming in the result. Okay. So why is this important? Well, I mean, I'm interested in the vertices of this mixed integer hull. So we know that vertices of this mixed integer hull are defined by linearly independent constraints, n linearly independent constraints, because we're in dimension n. And the constraint matrix looks like this. I mean, the I and the C come from our original polyhedron, and the W come from these mixed integer fibers that we have. Okay. But this second bullet point shows that C is linearly dependent on W. And we know that any vertex of the mixed integer hull has to live on one of these fibers, so it has to satisfy these W constraints anyways. And so when we try to find our linearly independent constraints that define our vertex, we only have to choose them from I and W, which is again a TU matrix, so then the vertices are integral. Okay. So I kind of went through this quickly, but the point is that this assumption that this B and T cover the columns, this trickles down to let us find a matrix W that we can use in our mixed integer relaxation. And this happens to lead to integral vertices. And so the integer hull is the mixed integer hull as well. Okay. So here is the lemma again that we just went through very quickly. And just as a shout out, I think it would be a very interesting question to see if, sort of given a set of columns C, and you assume that the largest determinant of C is bounded by delta, can you somehow combine this or can you prove that the integrality number of this is always the square root of the number of distinct columns? Okay, so I don't have time to get into all of this, but tomorrow Tim will be discussing some so-called sparsity results that show you that if you can solve an IP by only using this many columns anyways. So this already bounds the number of distinct columns we need. And so if we can somehow use this B and T lemma, perhaps we can reduce this IP to a MIP with even fewer variables. Okay, but just to keep pushing forward, so we can use this lemma to prove the following result. I mean, this is sort of a simple case. Suppose our IP has just a square constraint matrix. Okay, so A is n by n. Well then, for any choice of B, we only need square root of delta many integrality constraints. Okay, so why is this the case? Just to quickly run through it. Again, we can transform our polyhedron by unimodular matrices. So we can assume that A is in what's called Hermite normal form. If you're not familiar with that, just believe me that A can look like this sort of triangular matrix. And the number of columns in this last part is bounded above by delta plus log delta. And notice that A already fits into this format of the lemma. So all we have to do is find sets B and T that cover these delta many columns. So we could enumerate these columns, but that would lead to an integrality number of about delta. And what we do is we actually provide a construction. I don't have time to go into it here, but you can actually balance this B and T and make them both of size square root of delta. And then this leads to the result. Okay. And in some sense, this is, I mean, if we want to bound the integrality number using this lemma, then this is best possible, because if you have delta many columns, either the box B or the translation set T has to be O of square root of delta. Otherwise, you can't possibly cover everything. Okay. So in the last few minutes, I just want to mention what happens if we go beyond square matrices. Okay, so suppose we have a larger matrix, and I'm going to decompose it into, I'm going to decompose the rows into a square submatrix, which we just saw how to handle, and some additional rows A2. Okay, so this is just partitioning the rows. I mean, it would be great if we could somehow take these constraints and separate them completely and bound the integrality numbers of different polyhedra. This kind of seems like a pipe dream. I don't believe this to be true, but it would be interesting if there was some relationship like this. But to this end, we can actually show the following. So ignore this for a moment, but suppose the rank of A2 was equal to R. Then if we partition A in this way, we can actually bound the integrality number by this delta to the 1/2, which came from before. I mean, this is used to bound A1. And CR delta, what is this? Well, it's the number of, the possible number of unique columns that a matrix of rank R can have, where the largest minor is an absolute value delta. So essentially what this theorem is doing is it's kind of addressing the question. We are decomposing the rows of A and using this box and translation lemma independently. For the top, we have sort of our slightly more involved construction. And for A2, we just enumerate the columns. You can think of it this way. And this CR delta term, it was shown by some people at ETH in 2018 that this is bounded above by R squared times this delta squared plus log delta. Okay. So just to be a bit more precise, how do we prove this theorem? Well, we have this so-called concatenation lemma that if you do partition the rows of your matrix and you apply this box and translate lemma individually on each set of rows, then you can multiply them, essentially multiply them together, the sizes you can multiply and bound the integrality number. Okay, and again, that's where we get this. The 6 delta to the 1/2 comes from before, and the CR delta comes from enumerating these A2.
Joe, you should be wrapping up now. Okay,
thanks. So there is a technical hurdle that the number of rows of A2, or the determinant, can be much, much larger than this delta term we care about. But you can show that you can get around this. You can show that the columns of A2 are isomorphic to a nice matrix that we actually care about. Okay, so in the full version of the paper, there's a few other results. And in there, we also explore the question of, suppose you want to optimize in a non-zero direction. So you don't care about all all of your integer hull, just kind of one corner of it, how many constraints do you need? Through some asymptotic definitions, you can show that you can get away again with about square root of delta. I should say that in the current version of the paper, thanks to the IPCO reviewers, we were able to strengthen many of our results, but this inadvertently led to some inconsistencies in this section, but this will be cleaned up in the full version. And just for the sake of time, I'll stop and say thanks.
Are there any questions? Okay, I see a question from Menari Sharma. How can this be related to finding facet defining inequalities for the convex hull of a feasible region?
The convex hull of the integer hull, is the feasible region here the integer hull? Just to
Menardi, would you
clarify.
like to answer that? So I see a question in the chat, but not I'm not here.
I see. So that's interesting. I don't know how this goes into finding facets for the integer hull. It would be something that's interesting to explore. I know that these facets can be quite complicated, and we don't, yeah. As a short answer, I'm not sure if this immediately implies anything on how to compute facets for the integer hull.
Menardi asked, yeah, anytime anybody wants to speak in the question and answer session, you just unmute yourself and speak. That's the easiest way.
Okay, thank you. So, because in the first example that you showed, the one that you are calling integer hull looks like the convex hull for that feasible region, and the inequality that you are saying is sufficient, or the only inequality needed, I think in the beginning slides, is the facet defining inequality for that feasible region. Yeah, here, this one.
Yeah, that's right.
Okay.
I see.
No, so I was just wondering, so if this is related to finding facet defining inequalities for the convex hull of the feasible region.
So yeah, that's okay. Now I understand the question a bit more. Yeah, I mean, that's an interesting point. So if you do really find a matrix W that gives you this integer hull is equal to the mixed integer hull, then as I kind of alluded to in this proof, if you, I think this is the case, if you want to understand the facets, then you really only have to look at this W plus the original constraints. I have to think about this to be 100% sure, but it seems to go in this direction as you pointed out.
Okay, and just another question, can you repeat the importance of finding integrality number? You said something about how this can help in solving the problem. Means I missed that part.
Yeah, sorry. So as I guess as an integer programmer, one thing I'd like to do is if you give me a polyhedron, I'd like to find any integer point inside. And I'd like to do it as fast as possible. I mean, this feasibility problem. So if you give me, I mean, and I guess going down to this last result on this slide by Lenstra, you can find a vertex of these mixed integer relaxations, these mixed integer hulls. You can find it in about this time. That only depends on the number of integer constraints that you've imposed. So if you can, if the integrality number is very small, say, I don't know, square root of n, I mean, it's not always this case, but if it's, say, square root of n, as opposed to n, then you can find a vertex of this mixed integer hull, but the mixed integer hull is equal to the integer hull. So you're actually finding a vertex of the integer hull, which is also integer, in much less time. I mean, this is the big motivation for this.
Okay. But
Did that answer
do-
your
but-
question?
Yeah, very much. But another question in this line, but can we identify for what kind of problem we can have, smaller integrality number?
So yeah, I think we're out of time, but we can talk more about this offline. There's some interesting examples in this TU dimension paper, but for general matrices, I think, to the best of my knowledge, I mean, the constructions that we have here are the most general. But in terms of, yeah, we can talk more afterwards if you'd like.
Okay, no problem. Thank you, everyone. Yeah.
If everybody would like to unmute and applaud, please go ahead.